Alright, so today we're going to be going over projectile motion. So there's two equations we're going to need to know here, which is going to be our range equation. This is going to give you the horizontal range of projectile when shot. And when something is shot on a projectile, the only acceleration that's being done on it is going to be basically gravity. And then we're going to be using the free fall equation, which should be already known, as well as the velocity is equal to delta d over delta t equation, which should all be already known. And then we also have a new equation here, which is going to be another sort of, so this equation, when you plug it in, given the values, you're going to get uh equation of a parabola. So that hence why you see the x squared here and then you see a negative. So when you choose something in a projectile, it's going to have a shape of that. So if you remember on a graph, that type of shape would be an upside down parabola, which is why we have a negative and then we have an x squared here. And all of these values, the velocity initial, gravity, and then y initial is going to give us the coefficient and basically the rest of our parabola. Alright, so let's take a look at number 11. So a ball is thrown horizontally at 25 meters per second. It travels a horizontal of a distance of 50 meters before hitting the ground. From what height is the ball thrown? So, assuming also air resistance is negligible, we have to assume that the average velocity was 25 meters per second and it traveled 50 meters. So, if it traveled 50 meters and with the velocity of 25 meters per second, we're given that it takes 2 seconds to travel 50 meters. So now we know the time and we know gravity. So we need to figure out what height the ball was thrown. If you remember, we would use the free fall equation, which is t equals square root of 2 over g times square root of height. So we know t here and we know g, so all we need to do is figure out height. So let's start plugging in stuff. So we have 2 equals square root of 2 over 9.8, which is going to be g, times square root of height. And now all we need to do is simplify. So if we simplify for square root of h, we would square root of 2 over 9.8, we would do 2 divided by that, in which we would get square root of h is equal to 4.4. And then if we square that, we're going, because we want to remove the square root, we're going to get that h is equal to around 19.6, or rather 20 meters. So the height that the ball was thrown from is going to be 20 meters off the ground. So let's take a look at number 12. So a supply plane needs to drop a package of food to scientists working on a glacier in Greenland. The plane flies 100 meters above the glacier at speed of 100 meters per second. How far short of the target should it drop the package? So we could draw a little, I guess, diagram here. So that is the plane. This is going to be 100 meters, although this is not necessary, but and they want to drop the scientists are going to be like right there, let's say. So that diagram was obviously not necessary, but we want to use the free fall equation here, which is going to be, again, t over square root of 2 over g times square root of h. Because we know h here and we know g, we want to find out t first, and then we'll use another equation. So let's plug in everything for the free fall equation. So we're going to have t over 2 over 9.8 times square root of 100, because it would be falling 100 meters. And now if we calculate all this out, we're going to get t is equal to 4.5 seconds. So now what that gives us is that if when the plane drops the package from 100 meters off, the package takes 4.5 seconds to fall to the ground. So in order, if the plane, given that the speed it's moving at, in order for the package to drop on the scientists, or near them, not on them, we want the plane to drop it 4.5 seconds beforehand. So they're looking for how far, which is distance. They're not looking for time here. So in order to find distance, we're just going to do 4.5 times 150 meters, which is how fast the plane is moving. So 150 times 4.5 is going to give us an answer of 675, or approximately that. Yeah, 675 meters is how far short of the target should the package be dropped. Alright, so let's move on to number 13. So a physics student on planet Exeter throws a ball and it falls in a parabolic trajectory shown in the figure. The ball's position shown at t equals 1 second in the 1 second intervals in t equals 3 seconds until t equals 3 seconds. At t equals 1 second, what is the ball's velocity given this velocity component? So this is not on Earth, so we cannot use the gravity of the Earth to figure out the other velocity components, but we can use, I guess, common sense. So at t equals 2 seconds, we could see that the horizontal component is 0 because the ball is not increasing in the horizontal direction anymore. So at t equals 2 seconds, the velocity vector is going to be equal to 2 x component plus 0 y component. And it's still 2 as an x component because we have to assume that air resistance does not exist here. But gravity does. Gravity is the only thing working against the ball. Or yeah, ball. So now that we know that the y component is changing by 2 every second, we can figure out the rest of the stuff. So at t equals 10, t equals 3, the velocity vector is going to be again 2x component plus negative 2 y component. And that is because 1 second has passed, which means that the y component has decreased by 2 meters per second. And then we want to find the velocity at t equals 0 seconds. So again, we just do the same thing. So our x component is going to be 2 again, plus we want to add 2 to the y component of 1 second because the y component decreases for every second that passes. So our y component is going to be 4j. And that is going to be it for A. Let's take a look at B. So B is what is the value of G on planet Exeter? So we saw that the velocity on the y component or y-axis decreases by 2 meters per second. Yeah, 2 meters per second, like every second. So given that, that is the acceleration, or rather g. But gravity is going downwards, so g is going to be equal to negative 2 meters per second squared. And that is going to be our answer for B. What was the ball's launch angle? So we're going to take the component at t equals 0, and let's draw it in vector form. So we have an x component of 2, and then we have a y component of 4. So this is going to be our launch angle. If we use the vector rule and connect them, that is going to be the velocity at t equals 0 seconds, initial velocity. So yeah, 4 right here. So again, we know the opposite. This is going to be theta, which is going to give us our launch angle. We know the opposite component and the adjacent component. So again, we want to use tan negative 1 of 4 over 2, and that is going to give us our launch angle, which if you plug into a calculator, it would just be tan negative 1 or arctan of 2, which is going to give you a launch angle of 63.4 degrees. So that would be your answer, but if you were to write out in word form, it would be 63.4 degrees over the positive x-axis. And that could also be your final answer. All right, so let's move on to number 14. So in the Olympic shootout event, an athlete throws a shot with the initial speed of 12 meters per second at a 40-degree angle from the horizontal. The shot leaves her hand at the height of 1.8 meters above the ground. How far does the shot travel? So here we're dealing with projectile motion. Let's draw a little diagram right here. So let's say 1.8 meters is where it's shot. We're dealing with the projectile motion that goes below the y value in which it was shot, in which we're going to have to use the range equation, and then we're also going to have to use the free fall equation. So we're going to have range is equal to velocity initial squared times sine 2 theta over g. And then we're also going to have to use the free fall equation, which is going to be t equals 2 over g times square root of h. And then we're going to calculate the full distance together. So first, using the range equation, we're going to calculate the distance over from here to the point where the projectile is also 1.8 meters above the ground. And then the range here, we're going to calculate that using the free fall equation. So let's first use the range equation. So we have velocity squared initial, which is going to be 12 meters or 12 and squared times sine 2 theta, which is going to be sine 2 times 40, which is sine 80 over 9.8. And if you simplify that, you're going to get 14.5 meters. So this distance right here from when the projectile was shot to when it's 1.8 meters above the ground again, we're going to have is 4.5 meters. Now we want to find this distance, which we're going to add it to it. That's going to give us how far the shot traveled. So by this distance, we're going to have to use the free fall equation because we know the height that it's falling and we know the gravity. So we need to find the time that it takes to fall to 1.8 meters. Okay, so on second thoughts, the free fall equation would not work because I actually looked at it. And once we start falling from this point to this point right here, we're starting the fall with the initial velocity, in which a free fall doesn't work because free fall you must start with zero velocity, downward velocity at least. So what we're going to do is use the velocity final equation. As we know, we're going to know the velocity initial, the acceleration, and delta s. We're going to find velocity final and then find out time using velocity final and velocity initial. So let's start plugging into stuff into velocity final equation. So velocity initial is going to be basically the opposite of the y component at which it started. So the y component at which it started would give us, or we would calculate that by doing 12 times sine 40. So 12 times sine 40 is going to be 7.7 meters per second upward. So at this point right here, at the end of the projectile, our downward velocity is going to be negative 7.7. So our velocity initial is going to be negative 7.7 squared plus 2, and then acceleration is going to be 9.8, which is acceleration. And delta S is going to be 1.8 meters, which it's falling. And if we do some calculations, we're going to get velocity final squared is equal to 59.29 plus 35.28. And if we add those together, we're going to get velocity final squared is equal to 94.57. And if we square root 94.57, we're going to get that velocity final is equal to 9.724. So if you remember, acceleration is equal to delta v over delta t. We know acceleration, which is going to be gravity, and we know delta v now because we know velocity final. We could also round this to 9.7. So let's start plugging in stuff into acceleration equation. So Acceleration is going to be 9.8. Delta V is going to be 9.7 minus 7.7, which is velocity final minus velocity initial, over delta T. So we're going to have 9.8 is equal to 2 over delta T. And if we switch delta T and 9.8, it would be 2 over 9.8, which would give us a delta T of 0.204. So the time it takes for it to fall 1.8 meters at the end of the projectile is going to be 0.204 seconds. So all we need to do is multiply 0.204 times the horizontal velocity, which is going to be cosine 40. So cosine 40 times 12, and that's going to give us an answer of 1.87 meters, or 1.9 rather. And so 1.87 meters is this right here. So all we need to do is add together 14.5 and 1.87 meters, in which we could do it right here, 1.87 plus 14.5, which is going to give us an answer of 16.4 if you were to round it. So, and this was 1.876. So it would be 16.46 or 16.36, which we round to 16.4 meters, which is going to be a projectile distance. Now, there's a bunch of different ways to do this equation using other formulas and stuff, but I mostly prefer to use the range formula and then figure out the rest of the projectile using, for example, the velocity final equation. Although it's a little bit tedious, but for me, personally, it's a lot easier to understand, but there are other formulas out there that make this problem a little bit easier, or rather more clean to solve. So a rifle is aimed horizontally at a target 50 meters away. The bullet hits the target 2 centimeters below the aim point. What was the bullet's flight time? So the rifle, when it was shot, the bullet hit the target 2 centimeters below. So that means the bullet fell 2 centimeters in the time that it took for it to hit the target from 50 meters away. So for this, we could just use the free fall equation. T is equal to square root of 2 times g, 2 over g, times square root of h, because we know h and we know gravity, because the bullet obviously, it cannot defy gravity. So let's solve for t. So we have t equals 2 over 9.8 times square root of 0.02, because we're working in centimeters here, but we want to turn it into meters, which is a form of basic SI unit. So if we do 2 over, or square root of 2 over 9.8 times square root of 0.02, we would get t is equal to 0.064, which is going to be also seconds, which is going to be our bullet's flight time. That's how long the bullet took to hit the target. So we didn't need to use the 50 meters at all for that part, but we will for this next part. So for B, we want to find what is the bullet's speed as it left the barrel. So given again air resistance is negligible, which means that the rifle bullet is not being slowed down in a horizontal velocity stance. If you remember, velocity is equal to delta D or delta S over delta T. We know delta T. Delta T is going to be 0.064, and then the distance is going to be 50 meters. So we just plug it in. So delta D is going to be 50, and then on the bottom we're going to have 0.064. So all we need to do is 50 divided by 0.064, which is going to give us a velocity of 781.25. But since we're dividing here and 50 has two significant figures, our velocity or bullet speed as it leaves the barrel is going to be 780 meters per second. And that's going to be your answer for B. And your answer for A is going to be 0.064 seconds.